Hey there, this is Raimu, and this is part 14 of my Introduction to Rust series, taking it one step at a time. And today we're going to start talking about concurrency or multi-threaded programming, which is a pretty exciting topic, I think. So in this video, we're going to just be covering threads. In the next video, we're going to be covering futures, async await, which is another way to do similar things. But starting out with threads. So what are threads? Basically, when you write a program on most operating systems, you have a function that's called to start running your program. Usually it's called main. And that program, when it's running, has a stack. We've already talked about stack variables, so temporary variables, shared by different functions that are calling each other. So a thread is basically what we call the collective state of one CPU core executing part of your program. So when your program first starts out, you have one thread, which is executing your main function. And if you don't start any other thread or use a library that does, your entire program just runs on one CPU core or one thread. But these days, we have CPUs that have many cores. So if you only used one of them, you're not using all the CPU resources that your computer can provide. So we're going to go over how you create threads and how you handle cleaning them up, and how you coordinate the data and the work done by different threads in your program. So let's first start off with how we actually make a thread. So I have an example program here. What I'm showing here in our main is we're going to print something, and then we're going to set up a separate thread to do some work. In the meantime, we're going to be printing some stuff, doing some waiting of our own, and at the end, we're going to be joining or waiting for the thread that we spawn to complete, and then exiting our program. So let's go through this step by step. First, we're going to be printing a message, then we're going to be setting up a variable, and then here's the code in Rust that you would do to start a thread. It's in the standard thread module. It's called spawn. The spawn function takes a function or closure. As you can see here, it's the fn_once trait, and it can return anything and has no arguments. So we're using the move keyword to take possession of the steps variable because we're going to use it inside the closure. And the closure is going to return a string slice. So the return value of the string slice becomes the return value of the overall thread. So that's one form of communication between threads, is that a thread, when it's ending, can return a value back to the thread that's waiting on it. What's different about this closure is it isn't executed by the same thread or CPU core that executed this print line hello world and set up the steps. It's actually executed by a different CPU core. And we'll see that when we run this, when we have these sleep statements, this is a way we can have the thread just pause for a certain amount of real time. So in this case, this thread that we're starting is going to pause for a second. And then we'll see that this spawn to thread actually happens first before this print thread step. And then just to kind of illustrate also that they are really working in two different threads, we're going to have this main thread that spawned the other thread sleep for 2 seconds and print something. And the thread that we spawned is going to be printing a different message every second. So we'll see those kind of interlace. So to go over that again, this thread that we're setting up is basically going to step 5 times. Each time it's going to sleep a second and then print out what step it's on. And then when it gets done with those 5 steps, it's going to return this goodbye value back to the other thread. Meanwhile, the main thread is going to print spawn the thread. It's going to itself wait for 2 seconds so that we can see that while it's waiting, the thread that we spawn should print at least one message. And then we're going to have the main thread print a second message saying that it slept, and then saying that it's going to join the thread. Now, what is joining? Basically, whenever you spawn a thread, you get back something. That's something you can think of as a handle to the thread or a join handle. That's the name of it in Rust. That handle is really only useful for one thing, which is waiting for that thread that you spawned to finish. And when it's finished, you get back any return value that that thread returned. So in our case, this goodbye string would be what we get back here in this result. Because the thread has its own amount of time that it's running, this join doesn't stop that other thread immediately. It actually waits, or what we call blocks, or stops running until the thread reaches the end. If you wanted to actually kill that thread immediately, have it stop immediately, there's another way to do that, but we're not going to go over it. In this case, join, again, just going to wait until that thread that we spawned reaches all the way to the end and returns its return value. The reason why we have this unwrap here is because if we were to panic in that thread that we spawned, instead of getting this string slice out, we would get some kind of error. So join actually returns a result, which if it's okay, gives us the return value of the thread. Otherwise, if it panicked, we get the error that's associated with that panic. So unwrap it again is basically saying we expect it not to panic. We want the return value that we would get on a normal execution of that thread, and we're just going to print it. So running this to illustrate, we say hello world, spawn a thread, thread step 1, slept for 2 seconds, now joining thread step 2, 3, 4, 5, and then finally we have that thread return with goodbye. So you can see both threads are able to use that print line macro to print their status, and we can see the interlacing of the work between them. So overall, there's generally 2 different reasons why you'd want to have multiple threads in your program. I've already mentioned one, which is making full use of all your CPU cores. If you have some CPU-intensive work that you want your program to do, it makes sense to have your work split out between many different CPU cores and have them all done at the same time. Your program runs that many times faster. The other useful thing that you can do with multiple threads is if you have a thread which is waiting for something, like waiting for input, waiting for a file to be read or written, something that takes real time but not necessarily CPU intensive, maybe waiting for a packet to be received on the internet. Those are all things that while you're waiting, the thread is basically stopped waiting for it and can't do anything else. Now, as we'll see in the next video, there are tricks you can do to have a single thread handle multiple things simultaneously and not be blocked waiting for something like input or output. But in a primitive sense, when you're just using threads, each thread can only really wait for one thing at a time. So if you have multiple things you're waiting on, having multiple threads, one for each thing that you might wait on, is maybe a good idea. Okay, the next thing I want to talk about is how do we get data passed between threads? We already saw 2 ways in which we can do that. The move keyword used with the closure that we gave to spawn is one way to get data from one thread to another. Basically, any value that the thread which is doing the spawning wants to give to the thread being spawned, it can be captured by that closure, and with the move keyword, basically ownership is transferred to the new thread. The second way that we kind of shown here, how to get information from one thread to another, is the return value of one thread is given back to the thread which joins it. But let's say we're not starting a thread and we're not joining a thread, but we still want those threads to communicate with each other somehow. Well, how are different ways we could do that? Well, one way that we might try to do that is what was something that we learned previously, which is the reference counted pointer, something that allows us to share a value between different things. So let's say, for example, that we want to say not only do we spawn a thread, but with a step count of something, and say steps here, and to make sure that we're not simply copying that steps, let's make it reference counted. So RC new 5. And we're going to need to import standard RC for that. Because it's a reference, we're going to need to dereference it whenever we use it there. We're going to run into this error here. It's going to say that without RC, we can't safely send that between threads. Now, why is that? It turns out that the code which implements how we share that reference counter between copies of an RC isn't safe to be used simultaneously from 2 different threads. Looking at the error more technically, it says that the send marker is not implemented for RC. So what is the send marker? There are 2 special traits which Rust defines that have to do with objects being shared between 2 threads, and those are send and sync. We're running into the first one here, send. Now these traits are special in that they actually don't have any code associated with them. They're only used, as you might imagine by the name, as markers, tagging different types to indicate whether or not they're safe to be, in this case, sent between one thread and another. We'll run to sync in a little bit. So how would we share a reference counted object between threads? The answer is that there's a thread-safe version of RC called the ARC. So replacing RC with ARC, which comes from the standard sync library, we should be able to make another reference to that steps by doing something like this, where we make a clone of the original steps. Have that clone move into that thread, and the main thread keeps the original. We do need this main thread equals to be on the outside of that block because we need it back in the main thread. So we'll just remove the semicolon like that, put it there instead, run this, and we should be able to see that it works. Okay, so the program is back to working. So that's one way that we can share information between threads. ARC is different from RC in that it's shareable between threads, but how is it thread safe? Well, the A in ARC stands for atomically. The definition of what atomic means in programming is a little bit hard to get into, But a really simplified explanation is that something is atomic if it only takes one operation to change it. So you can imagine RC, the reference counted pointer. Perhaps it takes more than one operation between decrementing a counter and then freeing the object if that count reaches 0. Now, what if another thread was observing that reference counted pointer and incremented the reference count between when it was decremented to 0 and checked for 0 and when the object was destroyed? You might have the situation where one thread thinks the object needs to be destroyed because the reference count reached 0, while another thread just incremented to 1 and starts using the object. That would be pretty bad, right? ARC, atomically reference counted, basically gives you the guarantee that incrementing the reference count or decrementing it and freeing if it's at 0 is in one operation from the perspective of any other thread. So there's no chance of observing the internal state of that reference counted pointer in the middle of it being changed. You're either going to see it before or after. So therefore, it's safe to share that reference counted pointer between threads. So we now know that we can move data into threads by capturing those values and moving them into the closure that we give to thread spawn. We know that we can get data back out of the thread when that thread ends. And we know that we can share information between threads through an atomic reference counted value. Let's learn about another technique for sharing data with threads, and that's called the channel. A channel in Rust is a kind of message pipe where we can send objects from one place to another. They don't necessarily need to be from one thread to another. You can have a channel from one thread back to itself, but they are pretty useful between threads because you get two objects when you create a channel. You get a sender and a receiver. So let's see how that works. Let's say that we want to wait for that thread to start before sending it this step counter. So instead of making a reference counted number, let's create sender-receiver ends of a channel. A channel is defined in the multi-producer single consumer module of the standard sync part of the library. Kind of gives you a hint about what you can do with it. Multi-producer in this case means that this sender object can be cloned, and every clone of the sender basically is another way to get into this FIFO, which is kind of convenient. You have multiple threads that might send messages to a common recipient. The receiver end can't be shared between threads. You generally only have one thread which is receiving messages. If you wanted to have multiple receivers, you need to have multiple channels. Channels are one way, so the receiver always receives only. If you wanted to send back, you would generally make a pair of channels and send one thread, the sender for one and the receiver for the other. So in this case, we're going to have the receiver end get captured by the thread and show you how to actually do the receiving end. So instead of cloning steps here, we're going to go back to having just the thread being spawned here. And we're going to receive steps from the channel. The way we do that is we say let steps equal receiver dot receive dot unwrap. The receive can fail if the sender is closed. So if we were to like drop the sender here before the receiver tries to receive, it'd be an error. Now, just like the thread join, the receiver receive blocks until it gets something. So after spawning the thread, let's have it print out that it spawned the thread, and then we'll have it send the step count to the thread through the sender. Sender, send 5. We can remove this reference because we've now passed it by value. We're also going to get a warning that we didn't use the result from send. Send, just like receive, can return an error. In this case, we would get an error if the receiver got dropped before we're able to send that message. So in this case, we don't really care. We could unwrap that, but we don't even need the success value to it. So another technique we can do there is let underscore equal that, basically telling Rust that we're going to receive that result, but we're not going to do anything with it. We're tossing it. So running this program, we should see that we spawned the thread and we gave it the step count and it worked just like before. So if we modify this, for example, we could introduce another sleep here for a second and then have it say that we're sending the step count. Running this again, we'll see that it spawned the thread. The thread doesn't do anything until it receives that step count, and then it starts stepping. So I'm sure you can think of all sorts of interesting things you can do with channels. They're a really handy technique for getting data flow from one place to another, especially between threads. Okay, so we've covered how to send data into a thread through capturing it in the closure and how to send data back out as the return value of that thread. And we also covered how to send data between threads through a channel. And we've even shown how to share a reference through an atomic reference counted pointer. But let's say that we not only want to share a value between threads, we want to have the ability to have either thread mutate that value. As we've seen in the past, it's generally a problem in Rust when you have two things wanting to be able to mutate the same value. For example, you can't make two mutable references to the same value in the same lifetime. You can delay the borrow checking till runtime by using a RefCell, and we can share a reference to that RefCell and in two different places at runtime try to get a mutable reference. Can we use that same technique here in Rust? Well, let's try it out. So instead of using a channel to send the step count, let's go back to how we had it with an atomically reference counted value. And instead of having this for loop, let's try to modify the step counter in place, saying while steps is greater than 0, printing the step counter here, and then decrementing it, steps minus equal 1. So it's going to tell us that we can't mutate something through an atomic reference counter. So let's attempt to use interior mutability to solve that. Arc new RefCell new 5. We need to import standard cell RefCell, and we'll borrow the counter at the while loop there, dereference that, and again borrow the step counter when we print it. And finally, let's borrow mutably in order to decrement here. And in the main thread, we're going to borrow it when we print it. And we run into a problem. It's going to say RefCell can't be shared safely between threads. And this is the second marker trait that I mentioned, sync. Basically, RefCell can be sent between threads, but it can only be referenced by one thread at a time. And if you think about it, there is a little bit of a concurrency problem here. Now, what happens if we're in the middle of decrementing that step counter at the same time that we try to borrow it to print it out here? Just like RC, RefCell doesn't have a way to make these operations atomic. However, there is a type that does, which is basically the multi-threaded version of RefCell, and that's called the Mutex. So if instead of RefCell, we use Mutex, and we're going to need to import standard sync Mutex, and instead of borrow, we're going to turn those into lock. Now we do have to add an extra unwrap to the end of that, simply because lock returns a result instead of a straight out reference. And that has to do with the fact that if a thread panics while it has a mutex locked, then the lock gets basically broken, or what they call poisoned. Not relevant to this discussion, but essentially the equivalent of borrow is a lock with an unwrap. And then borrow mute also becomes a lock with an unwrap. And all of our compiler errors have gone away. Let's run this program, make sure it still works. And as you can see, it seems to be working. So how did this solve the problem, and why is it called lock? So if you've heard of Mutex and other programming languages, you might already know this. The way that Mutex achieves thread-safe interior mutability is it only lets one thread at a time get access. The name Mutex also implies how this works. Mutex stands for mutual exclusion. In other words, each thread that locks the Mutex has exclusive access to the value inside. While that lock is being held by one thread, any other thread that attempts to lock that same mutex gets blocked. Only when the thread that owns the lock releases that lock does the next thread that's waiting for it will obtain that lock. If you have multiple threads waiting for the same mutex, basically one of them is going to get it. Depends on the implementation of mutex, whether it's round robin or random. So in our case, each of the points that we're wanting to reference the steps is a potential place in which the thread may lock if another thread is using it. So the main thread is going to lock it here when it's printing it out, and the thread that we spawn locks it in 3 different places, one at the top of its while loop, one when it's about to print that thread step number, and another one where it's decrementing it. So there is a performance implication here. Whenever we have a lock, we have a point where a thread might have to stop and wait to get access to a resource. Depending on what the threads are doing at that time, that wait might be a long one. In our case here, it probably won't be a big deal because whenever we're accessing that steps, it's only to do something very brief with it. You have to be careful in that if you lock something and hold the lock for a long section of code, that could cause other threads to wait for very long amounts of time. So in general, these days, I recommend using Mutex as a kind of last resort, just like how we mentioned RefCell and interior mutability in general being sort of a tool of last resort in Rust. Prefer the other means of thread communication like channel, and just getting values in and out of the thread at the beginning and the end. So I know that might have been a lot to cover, but this is basically the tip of the iceberg for concurrency. This is showing how to make threads, how to get values in and out of them, how to communicate between threads. Programming with multiple threads can be a lot more complicated, as you can imagine. And there are a lot of things to think about in terms of the timing of the operations between threads. One thing that Rust has going for it is that the type system and the way threads are managed and how channels work and how mutex works, it does help to make concurrent programming relatively safe. It's very hard to trick the Rust compiler into a situation where you have some unsafe interaction between threads. Now, the cost of that, of course, is a lot of the time it's very difficult to write a Rust program that has concurrency in a lot of threads, because there are a lot of restrictions in the type system that you have to overcome in setting up your communication techniques. In the next video, we're going to cover an alternative way of doing concurrent programming in Rust, which is using what's called futures, sometimes also referred to as asynchronous functions. So I hope you're enjoying this series, and I'll see you next time.